Welcome everyone to another learning session. This is part two of systems design fundamentals sessions. As most of you know, systems design fundamentals is not only for clearing systems design interviews, it is also for understanding all other IT systems better, irrespective of what you are learning, whether you are learning cloud or whether you are learning just software architecture. Everywhere you will need to use these systems design concepts or components. That is why before jumping into systems design, we started with the systems design fundamental concepts. And we already discussed some of the important things in session one or part one, like HTTPS, SSL, databases, CAP theorem. All these things can help you design systems better and also help you understand things better whenever you are learning something like cloud or software architecture in general. So without wasting time, let us quickly get started with today's session. Systems Design Fundamentals 101 Part 2. And just in case, if any of you are new to these sessions and don't know me, it is good to start by knowing the teacher. So I'm Hartin Kanigatotu, and I've written a few books on cloud. I've also got this award of best 8th cloud computing book of all time. And I'm also a Microsoft certified trainer and have some expert certifications from Microsoft on solution architecture and DevOps. You can know all about me by going to this link hartin.github.io. And I had shared about how to create such a page in GitHub pages in the JIT 101 session. What are we learning as part of this tech series? In part one, we learned about protocols, client-server model, networking concepts, CAP theorem, behind-the-scenes working of HTTPS, and a lot of core things. And in part one, we had few coding assignments. We had few other kinds of assignments which you had all done and shared in our YouTube channel as comments. Others can also review them. And we had learned quite a lot of important things in part one. So now let us quickly go into part two. I'm just going through these pages so that it can refresh your memories on what we had learned in part one. And here comes part two, important characteristics of systems. So in part two, we will be learning important characteristics of systems. And these characteristics are ideal for a good systems design. And then in part three, we will be learning about the concepts that can help you achieve these characteristics. And in part four, we'll be learning a lot more. We'll be learning some of the existing components that can achieve these things. So these components may be using concepts in part three, or they may be directly helping us achieve the characteristics described in part two. So in this, we will be quickly looking into things such as availability and terms such as SLA, SLO, SLI, and then scalability, elasticity, latency, throughput, resiliency, fault tolerance, disaster recovery, RTO and RPO, and a few more other topics. As you know, this is not a master class. This is a class that help you look into those important terms and concepts from a high level. And based on your current knowledge level and based on your interest, you should be going deeper into each of these, maybe a Google search. And if you are not able to understand any of these in detail, you are always free to ask in our systems design discussion WhatsApp group. What is this availability? So availability is the percentage of time within a given period a system is available to perform its intended functions. Availability of a system is dependent on how resistant the system is to failure. And availability can be increased by using techniques such as redundancy across servers or across zones or across regions. Whenever we look into characteristics of systems, availability is one of the most important ones, because If the system is not able to perform its intended functions, then whatever else it do, it does not matter, right? Can you quickly tell me some of the things that can affect availability of a system? Okay, natural calamity, power failure, disk failure. So natural calamity usually happens in a particular region, right? So to overcome that, we can use redundancy across regions. Then other one, power failure. So power failure again, it will be within a particular zone or a mini region in general, or even worst case because of a natural calamity, it can happen across a whole region. So in that case also, by replicating your system or by using redundancy, you can have your system available. And then this failure also can be overcome by replicating your system across different servers or server racks. High resource consumption. Some of the high resource consumption scenarios will be considered by your application team itself. They will be doing things such as stress testing or load testing and all to make sure, okay, your system is able to handle the load that is expected of it. What are situations in which it may have to handle a load that is not expected? What if somebody decides to attack your system? Yes, DDoS. DDoS stands for distributed denial of service. DOS or denial of service means you send lot of requests to a system more than its defined throughput. We'll see what this throughput and all in a future slide. In simple terms, more than what it can handle. Say the system can handle 100 requests per second, and if somebody is sending 1000 requests per second, it can lead to the system becoming not available to the actual intended users. Denial of service or DOS generally happens from one system, and with today's capabilities of servers, they can easily prevent it. So they can easily say that, okay, from this IP, if more than n number of requests comes within this duration, do not allow. But then hackers also became more intelligent, and they did something called as distributed denial of service. So basically, all these requests will not be coming from only one IP or one system. It will be distributed, and it will be coming from across the globe, so that the IP-based approach may not work. And many systems and many cloud providers have ability to handle these things, especially using AI, ML, and all those fancy things. And some of these services may be paid, some of these may be free. We will go deeper into those things as part of our cloud learning. Okay, there is no limit to how things can go wrong. And sometimes we can prevent some of the availability issues with redundancy. And sometimes we can prevent with auto scaling. We'll see what scaling is and then auto scaling is soon. So quick question. How many of you know about these terms called SLA, SLO, and SLI? And how is it related to availability? Okay, service level agreement. Okay, agreement with the client or customer. Okay, another question. Is 99% availability a good thing or a bad thing? Okay, people are telling it is a good thing. So now tell me, based on your mathematical knowledge, how much downtime can a system with 99% availability have per year? Okay, people are telling 3 to 4 days. So is it a good thing or a bad thing? So availability is usually stated in nines of availability, such as 99%, 99.9%, 99.99%. So this is a industry standard. So when you say 99%, it is also called as 2 nines of availability. When you say 99.9, it is also called as 3 nines of availability. When you say 99.99%, it is called as 4 nines of availability. What if it is 99.95%? It is 3.5 nines of availability. And some systems may have 6 nines, 7 nines, or even 11 nines of availability. Okay, as an unofficial assignment, find out a few systems on cloud or on premises which has very high availability, more than 7 nines. And 99% or 2 nines means the system can go down 3.65 days per year or 7.31 hours per month. And 99.9% or 3 nines means the system can go down 8.77 hours per year or 43.83 minutes per month. And 4 nines means the system can go down 52.60 minutes per year or 4.38 minutes per month. So now, based on this newly acquired knowledge, answer again, is 99% availability good or bad? So now everybody are telling it is bad, but the answer is depends. For some systems, it may be okay to have that availability. And for some systems, it may not be okay. It depends on the situation. Because whenever you are increasing this availability to 99% or 99.9% or 99.99%, you will be doing a lot more things and you will be increasing the cost significantly. And for some systems, it may be okay compared to the cost. Okay, compared to the cost, it may be okay to have a little bit of downtime. Maybe those systems also have offline processing. So the answer is in general depends. That is what you will have to do as part of your systems design exercises or while preparing your architectures. So a quick assignment. List down applications for which you think 99% availability is okay, and list down applications for which you think 99% availability is not okay. And from now on, I am planning to introduce more prizes for people who actually answer this first in the YouTube channel. So you'll have to wait for when it will be available, and then immediately you'll have to do it. Little bit of fun. Availability in general is stated and tracked in terms such as SLAs, SLOs, and SLIs. SLA stands for service level agreements we make with the customers. SLO stands for service level objective and is the objectives set by teams to meet their SLIs. And finally, SLI stands for service level indicator and is the real data or numbers about your availability. SLO is the objectives set by the teams. So I cannot simply say that, okay, I will give you 99% availability and then my system will not automatically provide those things, right? So I need to have some objectives to make sure I meet that SLA, whatever I had promised. And also, you need to have some kind of indicator to track these things. And SLA stands for service level indicator and is the real data or numbers about your availability. And as the next assignment, you can Google out various examples of SLAs, SLOs, or SLIs that you can find online for various cloud services or products. Example, VM availability in Azure Cloud or AWS Cloud. So search for these terms, try to make sense of it, and then you comment. That way you will be learning and also you will be helping others. Why I am giving these assignments is mostly because whenever you are searching for a thing in Google, you are not only finding the answer to that thing, you will be finding a lot of other things that are related. All those related knowledge can be very much useful in increasing your breadth of knowledge. I've told you in the previous session, right? As an architect, you need to have depth of knowledge and breadth of knowledge. And if you don't have a good breadth of knowledge, what will happen? You will run into a problem. Can somebody quickly tell me that problem that you will run into if you do not have a good breadth of knowledge as an architect? It is called as a golden hammer problem. Okay, I'm not going to explain what golden hammer problem is and how it is relevant here. The next two characteristics, scalability and elasticity. So scalability is the capability to adapt and perform well under an increased or expanding workload or scope. When we discussed about availability, some people told about increased load, right? What will a system do, or what should systems do when they have increased load to keep up the availability? They need to scale. You need to dynamically adapt to that new load. And how do systems adapt to that new load? That is through something called as elasticity. So elasticity is the allocation of required resources to meet current needs. In general, scalability is generally achieved through elasticity. So scalability is that capability of that system to perform well under an increased or expand workload or scope, and it is achieved through elasticity. When it comes to cloud or real world, it means that you have n number of machines and you have more load. So what are the options you have? You can either have more machines to handle that load, or you can increase the capability of existing machines. So having more machines added automatically is also called as auto scaling. Many cloud providers and systems has this capability of auto scaling. You can define, okay, when my load increase the number of systems that handle these requests from A to B, and it will be done automatically. That increasing part is called as elasticity. Most cloud providers have something called as auto scaling. So elasticity and scalability are kind of related also. So how many of you know these terms called as vertical scaling and horizontal scaling, or scale up and scale out? Vertical scaling or horizontal scaling, which of these is called as scale out? Horizontal, right? So scale up means vertical, scale out means horizontal. Scale out means you will be adding more systems. Scale up means you will be increasing the capacity of existing system. Maybe increasing RAM, maybe increasing CPU capacity. So which of these is more appropriate with respect to auto scaling? Is it vertical scaling or horizontal scaling? Or is it a scale up or scale out? Okay, we have answers vertical, we have horizontal, we have both. So what is this auto scaling? Auto scaling means whenever you get an additional heavy load, your system has to automatically adapt, right? So whenever somebody is giving you extra load, is it practical to increase the RAM or CPU of your machine before that request is processed? Or is it more easy to add more systems that are ready to added or processed? Horizontal, right? So scale out or horizontal is always the one that is most appropriate for auto scaling. Vertical scaling or scale up means replacing servers with more capacity ones or increasing its capacity. Horizontal scaling or scale out means adding more servers and processing in parallel. Dynamic scalability or elasticity on cloud is generally based on horizontal scaling. Okay, one question again for you. Which is easier from an application developer's perspective? Vertical scaling, or also called as scale up, or horizontal scaling, also called as scale out? Some saying vertical, some saying horizontal, but mostly people are telling vertical, and it is right. Vertical is more easier because you don't have to worry about scaling. Because if your system is not performing, you'll be manually changing your configuration. So people learning Azure Cloud alongside this will know, right? If you go to the PaaS service called Azure App Services, you have option for scale up and scale out. Scale up means you'll be changing the configuration or changing the app service plan with higher RAM, CPU, etc. And horizontal scaling or scale out means you'll configure, okay, increase my number of servers to maybe 3 or whatever you want. But for effective auto scaling or effective horizontal scaling, your application also needs to have some features. Like if your application is stateless, it is better for auto scaling. And if your application has a state such as caching or anything, all the requests from a particular client ideally has to go to one particular server itself. That is also sometimes called as sticky sessions and all. When we learn about hashing, which is one of the techniques behind these load balancers who actually send your request to the machines that are there in your auto scaling set of machines, we will see some hashing techniques that can make sure that as much as possible requests go to the same server itself. And there are also some that do not care about these things. It is a very interesting topic to discuss about hashing. We will see them when we see hashing in our part 3. So answer is vertical scaling. So next question, which is easier from an auto scaling perspective? Everybody answered it already. It is horizontal scaling. Latency and throughput. So latency is a time delay between the cause and effect of some change in a system. There could be a lot of examples. For example, a time taken for a packet to go from client to server and then a response from server to come back to client, or time taken to read from a memory or a disk. And whenever you are working with the systems design, you need to have some vague idea about how different operations are ordered with respect to latency. For example, reading from memory will be faster than reading from an SSD. And reading from an SSD may be faster than reading from a network without considering the distance. And it may be still faster than reading from a traditional hard disk. And all these will be faster when you consider latency of a round trip. Basically, you send a request to another side of the globe and then request coming back. So all these things you'll have to keep in mind, because sometimes you will need to decide on whether I need to keep things in memory or whether I need to keep things in hard disk. Lot of decisions you'll have to make while preparing architectures or working on systems design. And everything had its trade-off, right? Keeping in memory is definitely faster. Memory means RAM. But there will be definitely some limitation. You cannot keep everything in memory, right? And what is this throughput? Throughput is the work done in a given period. So the number of requests a server can handle in a given period, number of packets processed within a given period. So basically, the work done by a system in a given period, or its capacity. We discussed earlier, right? If a system can handle only 100 requests per second, then that is its throughput. So if you send more than that, the system will not be able to handle. So key question, which of these are preferred? Low latency, high latency, low throughput, high throughput? I need two answers. Okay, low latency and high throughput. Low latency and high throughput is always preferred. So we can increase the throughput by scaling, vertical or horizontal. And network latency across regions can be reduced using CDNs or content delivery networks. There are many CDN providers such as Akamai, Verizon, and then Azure, AWS, etc. have their own CDNs. So basically, these content delivery networks or CDNs cache data closer to a user so that they can get those data faster than always going to server, maybe on the other side of the globe. And latency and throughput may be related, but may not be always be correlated. So latency and throughput can cancel the effect of each other also at times. Example, benefit of low latency network may be cancelled by a low throughput server. Imagine that I have a low throughput server, but I have a very low latency network. So even if the network is of low latency, my request goes to server and server will have to process, and then only it will give me back the response, right? So even if I have made this network as a low latency network, if the server is having a low throughput, effectively that low latency network does not make much sense. Okay, so that is why low latency and high throughput are kind of preferred together. Resiliency, fault tolerance, and disaster recovery. How many of you understand these terms? Part 2 is all about introducing you to these terms. Some of these you may be knowing, some of these you may be hearing it for first time. But to understand part 3, part 4, and then future systems design or future preparing architectures, all these terms are important. So resiliency is the ability to maintain an acceptable level of service in the face of faults and challenges to normal operation. This kind of related to the availability also, right? But there is a very small difference with resiliency. Only the uptime in response to a failure is considered, but in high availability, the performance and uptime are both considered. So it has to do the intended function, right, with availability. So resiliency is the ability to maintain an acceptable level of service in the face of faults and challenges to normal operation. Again, these are very much related. So you will not be asked in general about the differences between resiliency and availability. But the important things to consider here are fault tolerance and disaster recovery. So fault tolerance tries to achieve a resiliency by ensuring that servers or services remain available even if some fail. And disaster recovery tries to achieve resiliency by maintaining or quickly resuming mission critical functions after a failure, usually through failovers. In fault tolerance, service continues after failure. In disaster recovery, service may be interrupted but recover faster. So in fault tolerance, say that you have 3 systems parallelly handling the request, and if one of them fail, the other 2 can continue to work. Again, concepts or tools such as load balancers that we will learn later plays a very important role. Basically, the load balancer will have to somehow know that, okay, one of the servers is not working anymore, and it should route all these requests to the working ones. In summary, fault tolerance means the system will continue to work even if some of the components fail. What about disaster recovery? It means the system may go down, but immediately it will be brought back, maybe in another region. Okay, there could be some downtime in case of disaster recovery. And when it is related to a cloud, most clouds or most cloud providers have this concept of regions, which is kind of a geographical area. And within those regions, they will have this concept of availability zones. Different zones will have different sets of machines with the different power and all those things. So in general, within a region, most cloud providers look for fault tolerance, and across regions, they look for disaster recovery. If there is a disaster in a particular region, then the alternative is to bring the server up in a different region. Those details we can definitely explore more when we learn about any cloud provider such as AWS or Azure. So we have groups learning Azure, we have groups learning AWS, and we have this group who is learning systems design without looking into any cloud in particular. So you can decide which cloud provider you want to go next, just in case if you want to go. Next, 2 very important terms, RTO and RPO. Because as an architect, so these are 2 very important things I ask the teams before defining an architecture for them. Because one of my roles as a cloud architect within my current company is to help other teams move to cloud. So before deciding on whether they need 2 availability zones or across region replication and all, the key question I ask them is, what is your RTO and what is your RPO? Okay, recovery time objective and recovery point objective. So do you remember earlier when I asked you a question, whether 99% availability is good or bad. Initially, everybody said good, and then later, everybody said bad. And then I said, depends, right? It depends on your RTO and RPO to some extent. So these things define how much downtime is okay for you, and also how much data loss is okay for you. No data loss and no downtime is always good to have. But if that was the case, then there won't be any need for any architects, right? You always can go with that option only. But as an architect, you need to make trade-offs between performance and cost, maybe between performance and security, maybe. There are a lot of things to consider, right? Recovery time objective, or RTO, is the targeted duration of time and a service level within which a business process must be restored after a disaster or disruption in order to avoid unacceptable consequences associated with a break in business continuity. Without affecting the business, how much downtime is okay. Recovery point objective is the maximum targeted period in which the data might be lost from an IT service due to a major incident. RPO is dependent on the frequency in which backups are taken. So if your backups are taken every 1 hour, then maximum data you can lose is for that 1 hour, because otherwise it will be a part of your backup. Okay, all these things you need to understand and get from the business before you can prepare an architecture. So do not overdo any of these things. If the system is okay for 3 days of downtime or 4 days of downtime per year, then you should always go for a similar SLA or similar architecture. So based on this, you define your SLA, and based on your SLA, you define your architecture. Those people learning any cloud like AWS or Azure will know, right? So many services or service combinations will have various SLAs as defined by your cloud provider. For example, Azure says, okay, if you use one virtual machine, then you will get maybe 99% SLA. If you use two virtual machines across two availability zones, maybe you get 99.9. And if you use it across regions, you will get a better one. So why are these providers giving different SLAs? Why can't they just give super high SLAs for everything? Because everything involves a cost, right? So sometimes you'll have to take the decision as an architect by calculating the trade-offs between the cost and performance or other parameters. And there are also other important characteristics like global reach. So sometimes your business may have to be available in multiple countries, maybe because of compliance reasons. And for that, going with a cloud provider is a very easy solution. A new company or a new startup may not be able to go to every country and set up a data center just because of compliance requirements. They can take a space or rent a space from a data center that is already available in that region, and then they can use it. So cloud actually helps you a lot in your global reach scenario. And another characteristic of your system is agility. How many of you have heard about this waterfall and agile? Your system should be able to adapt changes very fast. There also, a cloud provider can really help you, because in on-premises, what will happen if you buy a server and if you feel like, okay, this server is not going to work for me, then selling that server and buying another server is going to be a nightmare. Definitely you will incur losses. But in cloud, you can just stop using that server and then you can start using something else. When you stop using that server, you'll not be charged for that again. So cloud is a answer for agility. And predictive cost. As an architect, you always have to be accurate about your cost calculations, right? This is many software or many cloud providers provide you ways to calculate or predict cost. If you see the example of cloud providers such as Amazon and Azure, they have their own pricing calculators. In Azure, you have a pricing calculator that help you predict costs with respect to services. And also you have a TCO calculator or total cost of ownership calculator that help you calculate cost savings with respect to migration. So how much I am going to save if I move to cloud. So these are all provided as a add-on by your cloud provider in most cases. And finally, security. Security is also a very important topic. We learned about HTTPS in part 1. And we'll have more sessions focused on security after the initial 4 parts. You have things such as defense in depth, zero trust architecture. How many of you have heard about these terms, defense in depth or zero trust architecture? Okay, part 2 was a very small part, but it has a lot of important terms. And these terms, if you understand properly, then you will understand part 3, part 4, and then you can become a good architect. As an assignment, go to the WhatsApp group and you should send a message with every term you learned today. You should send one term per message. That is first rule. Second, you shouldn't be sharing anything that was already shared by other person. So if you share and then see that, okay, somebody else has shared it already, then you can delete yours and allow the other person's one. So let us start with this small and fun game in our WhatsApp group, and let us all learn together with a little bit of fun. Okay, so compared to part 1, this was a smaller session, but all the terms that we discussed in this smaller session are very much important for understanding the next 2 bigger parts. You'll be learning a lot of important terms and concepts with respect to caching, with respect to hashing, with respect to load balances, with respect to streaming, polling. A lot of interesting things are coming up. So try to attend these sessions live and try to answer all questions live. Try to ask all doubts live. And that way we can learn much more faster. And let us all be good architects, and let us all excel in systems design. Thank you all for joining, and then see you in next class.